Good morning, everyone. Today we shall continue in our lecture series on elementary modern physics. So today we shall be looking at the following: the Lorentz transformation. Under that, we shall be discussing simultaneity of events, the Lorentz um, Fitzgerald contraction, time dilation, and relativistic velocity transformation. Lorentz transformation. Recall in the previous lecture we talked about the Galilean transformation, and then also we talked about the postulates, Einstein postulates, and all that. That for known as for special theory of relativity. If you have not watched the lecture on that, please refer to the week one lecture on that, so that you can grab what we shall be discussing now. So today, like I said, we're going to be discussing Lorentz transformation. So Einstein postulate of special theory of relativity required that the Galilean coordinate transformation be replaced by Lorentz coordinate transformation. Of course, coordinates, um, just see it as a space, defined by the Cartesian coordinate, that is x, y, z. You have the x direction, y direction, and z direction. And of course, the Galilean, of course, there are limitations to the Galilean transformation, and then now from the theory of special relativity, the Lorentz transformation tends to make some modification to the Galilean transformation, which we discussed in the previous lecture. So the transformation are as follows. We have the equation 1, which is x prime, sorry, equals to gamma x minus vt. Then x y prime equals to y, x z prime equals to z, t prime equals to gamma into t minus v all over c square x. Um, we can see that the transformation is on the x bar and the t, that's the time coordinate, and the x, because here we are assuming that the motion is in one direction, which is x. So where gamma is given by equation 5, which is equals to 1 all over root of 1 minus v square all over c square. So it's just a transformation just to replace those coordinates as we can see on the screen. Then work example to see how we can apply that. Consider two uniformly moving systems whose origin coincide at time t equals to 0. Let a flash of light be produced at the common origin. Each observer is justified in considering himself at the center of an expanding sphere of light. Experiment has revealed that obtained each of them obtained the same value of c for the speed of light. The Galilean transformation does not give this result. So by trying a modification, the modification is shown there. X bar equals to, from the Lorentz transformation as we have discussed before. Then find the expression for gamma so that the transformation is in accord with Einstein's postulate. So this question is just to give a modification to the Galilean transformation. Here we have the solution. The equation of the observed wavefront will be, we have x squared plus y squared plus z squared equals to c squared t squared, which is equation 1. We have the equation of the observer in the system moving with respect to the source will be, so the other one is the observer, the stationary observer, while this equation 2 is for the moving observer. We have x bar square, x prime square, y prime square plus z prime square equals to c square t prime square. C is a constant, is the speed of light, so it cannot carry prime. Then subtracting equation 2 from 1, we get, when you subtract that equation 2 from 1, you get supposed to be 3 there. And then eliminating the prime coordinates with the help of the given transformation we have. So when you try to eliminate of course, when you eliminate and solve mathematically you arrive at the last equation there. Yes, you arrive at the last equation there. Then also by simplifying, we have this using binomial expansion, which if you solve correctly, you arrive at the final result, and then which the gamma is equals to 1 all over root of 1 minus v square all over c square. You can check that, you can solve mathematically. I think the mathematics there is easy to apprehend. Then the next thing is simultaneity of event. So two events are simultaneous to an observer if he measures that the two events occur at the same time. Here we are talking about time coordinate now, because here we are considering space and time as being together. You cannot separate them. Then with classical physics, when one observer determines that two events were simultaneous, then t is equals to t prime. From Galilean transformation, every other observer would also find that the two events were simultaneous. That is what we learned from the Galilean transformation. That's from the classical perspective. There is one universal clock in the whole universe, but Einstein is coming to say no, time is relative. And so in relativistic physics, on the other hand, two events that are simultaneous to one observer will in general not be simultaneous to another observer. So because time is relative, it depends on the motion of the observer. If the observer is stationary, he will measure time differently from another observer who is in motion. And that is what the relativistic perspectives try to explain. So let's take an example to see, for us to better appreciate that. So observer 0 notes that two events are separated in space and time by 600 meter and 8 times 10 to the power of minus 7 seconds. How fast must an observer at 0 prime be moving relative to 0 in order that the two events be simultaneous to 0 prime? The stationary observer will start its measurement from 0, while the moving observer will measure at 0 per. So here both the coordinates are synchronized, starting at the same time. That's what it means by that. So how fast must an observer 0 prime be moving relative to 0 in order that the two events be simultaneous? In order that the two events will be the same, will have the same time, sorry. So T1, here we have T1, which is one of the observer, the first observer, whose measure 0 or O. Of course, T1 prime is equals to gamma into T1 minus V equal over C square X1, and then T2 will measure similar, which is X2. Then subtracting 1 from 2, then we equate it to C. Of course, if you do that mathematics correctly, we will arrive at T2 prime minus T1 prime equals to that, where T2 minus T1 is equals to 8 times 10 to the power minus 7 seconds, and X2 minus X1 is equals to 600 from the question. So if the events are simultaneous to 0 prime, then T2 minus T1 will be equals to 0. Hence, the equation will give 0, because T2 minus T1 equals to 0, then hence the equation will give what we have on the screen. And then solving mathematically, making V the subject of the formula, and all that, we arrive at V equals to 0.4 C. That is to say, the 0 prime must be moving at 0.4 fraction of the speed of light for the two times to be simultaneous. So The next one is the Lorentz Fitzgerald contraction. So if a body is at rest with respect to an observer, its length is determined by measuring the difference between the spatial coordinates of the endpoints of the body. Since the body is not moving, this measurement may be made at any time, and the length so determined is called the rest length or the proper length of the body. So if however the body is in motion, then the spatial coordinates of the endpoint of the body must be measured at the same time. Because if you don't measure them at the same time, you won't get the proper length. So the difference between these coordinates gives you the length of the body. Sorry. So now let us consider a ruler parallel to x bar x prime axis to be at rest in the 0 prime frame. So we wish to determine how the length measurements of 0 and 0 prime are related to each other when 0 prime is moving relative to O or relative to 0 with the velocity v in the x to x prime direction, in the xx prime direction. So if we designate the ends of the ruler by A and B, that is the first, the one end of the ruler is designated by A, while the other end of the ruler is designated by B. Then from the inverse Lorentz transformation, which is given as that SB prime minus SA prime will give that what we have on the screen. So the difference is equals to L naught, which is the proper length of the ruler as measured by 0 prime. So if xb minus xa are measured by 0 at the same time, so that tb minus ta is equals to 0, then the difference is sb minus xa is equals to L, will be the length of the ruler as measured by 0. Hence the equation becomes, so if we solve mathematically, we have L naught equals to L all over 1 minus v square all over c square, talking about the proper length, and then of course the 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 length of the ruler, that's the difference, the other length, which is L. Now that's for the other observer, will be L equals to L naught into the square of into root of 1 minus v square all over c square. So since v is less than c, since velocity of the observer is less than the speed of light, then we have that the root of 1 minus v square all over c square is less than 1, and so L equals to L naught, and so L will be equals to L naught. This means that the length of the moving ruler will be measured by 0 to be contracted. This fact that L is less than L naught is called Lorentz Fitzgerald contraction. So length, it depends on the observer, because we know that time is relative, space is relative also. That is to say, if an object is moving, of course it will measure time differently, it will also measure length differently, a lot of things will be measured differently. So what the Lorentz Fitzgerald contraction is trying to let us know is that length is also relative. That is to say, it depends on whether the observer is stationary or is moving. So if it is moving, it will of course measure a different length. So you can see the length of when the object is moving or when the observer is moving will be shorter or will be contracted than the actual length, will be contracted by than the actual length. So let's take One example. Sorry. So an airplane is moving with respect to the Earth at a speed of 600 meter per second. Its proper length is 50 meter. By how much will it appear to be contracted to an observer on Earth? So an aeroplane flying in the sky, of course, with respect to Earth at a speed of 600 meter per second. Its proper length is 50 meter. So by how much will it appear to be contracted to an observer on Earth? So somebody observing it on Earth, how will that how much length will it measure? So the solution we have from the question, the actual length of the aeroplane is 50 meters and is moving with a velocity of 600 meter per second. And of course, the expression for the length of from the length of the observer 0, we have Lx equals to L naught, that which is into 1 minus v square all over c square. Substitute our values in and we get 49.9999999. So we subtract it from um, what we the actual length, we get 1.0 times 10 to the power of minus 10 meter. So that is to say the length of the aeroplane is contracted by 1.0 times 10 to the power of minus 10 meter for an observer on Earth. An observer on Earth will measure this length for the plane. Then another example, a cube has a proper volume of 1000 centimeter. Find the volume as determined by an observer 0 prime whose who moves at a velocity of 0.8 the speed of light relative to the cube in a direction parallel to one edge. So the solution. So the solution now, the observer measures an edge of the cube parallel to the direction of motion to be, still using the same expression, L equals to L naught into 1 the root of 1 minus v square over c square equals to, you substitute the value given in the question. So after solving we get 6 centimeter, where the length of the other edge are unchanged. Hence L prime y equals to L, y other the other length of the other edges are unchanged. So that is L prime y is equals to Ly equals to Ly is Lz also and all that, which is equals to Lz is equals to 10 centimeter. So they are all equals to 10 centimeter since they are unchanged. So therefore the volume is equals to, normally volume is length times breadth times height. So we have length of s prime Ly prime times Lz prime should be 6 times 10 times 10 because all the other coordinates are unchanged. And our final answer is 600 centimeter cube. The unit is in cube because what we calculated is volume and volume is centimeter cube. So then the last one is the time dilation or time dilation. Here let an observer say 0, or O observes two events A and B that occur at the same place in his frame of reference. The time interval between these two events can be determined by 0 with a single clock. This time interval Tb minus Ta equals to change of T by T naught as measured by O with his single clock is called the proper time interval between the two events or between the events. Now consider the same two events A and B as viewed by a second observer O prime moving with a velocity v with respect to O. The second observer will determine that the two events occur at different locations and will therefore have to use two different two different. We use two different. So properly synchronized clock. We use two different properly synchronized clock to determine the time separation. That is t b prime minus t a prime, because the change in t between the two events. So here it means that time time is not constant. So time is also relative from the relativistic perspective. So from Lorentz time transformation, we have t prime tb prime minus ta prime. Let's change that. So you plug them in and you solve mathematically. You arrive at changing t prime equals to that expression. Since o is since o determines that the two events occur at the same location, x minus ab is equals to 0. So it's because the event is occurring at the same location, then the difference of that is 0. And of course we arrive at so it means the other part of the equation, this will be 0. So if this is 0, then the whole of this will be 0. So we'll be left with change in t naught all over root of 1 minus v square all over c square. So this is the expression for time dilation. And c0 is equals to is determined that the two events occur at the same location. Thus we have that, which is in the previous page. Since 1 over root of 1 minus v squared over c is greater than 1, therefore change in t prime is also greater than change in t. That is, the moving observer will measure more time than the stationary observer. So this fact that t prime greater than t is called the time dilation. So time measurement is relative. This is to say that the time interval between the two events are relative. So thank you very much for your audience. I want to believe you all enjoyed the lectures. See you in another segment of the lecture. Thank you very much.